Hi, PolyConf. I'm really excited to talk to you. So a lot of these talks have been about programming languages. And this talk is not going to be about programming languages mostly. Instead, we're going to talk about bugs everywhere. Who writes programs with bugs? Yay! So I want to talk to you about my favorite things, my favorite ways to debug programs, and my goal for this talk is for you to come away with like a new way to debug a program. If I've done that, then I'll have succeeded. So normally when we debug programs, we have all kinds of programming languages. One thing that happened to me recently, this is like my favorite thing, is someone came up to me and they were like, hey Julia, I'm having this like network performance problem in Erlang or in Elixir. And I was like, I don't know how to use Erlang or how to use Elixir, but I could help them debug it anyway, like a wizard. So I'm gonna tell you how you can help people debug programs in a language that you don't know. This talk is mostly going to be about Linux. So I could debug their program on my computer, but they had a Mac and I couldn't debug it on their computer. And the kind of like philosophy I want to talk about here is to treat your program like it's a black box. So normally when you're debugging a program, who will like look at the code in their program when debugging? Normally, you might add print statements. Would you say that you would need to like know the programming language? No, it's unimportant. Instead, we're going to talk about how to like be a wizard and how to debug anyway. What do you know this program? Top. So this is Top, and Top doesn't care what language Chrome is written in, right? So like you know about looking at programs where you don't care about the programming language, because you can look at like how much CPU they're using or whatever. You can kill them. You don't care that like Python is written in Python or whatever when you're killing it. You just kill it and then it's dead and that's it. So in this talk, we're gonna talk about like wizard school. By wizard school, I mean operating systems. By systems programming, I mean operating systems. And then we're gonna solve a few different mysteries. Like we're detectives. So let's do wizard school. I want to talk a little bit about what operating systems are. Probably you know this already, but like a few years ago, I had been using Linux for 9 years, and I realized that like I didn't know what my operating system did. I was like, I know it does very important things, but what? So you may have gotten this interview question before. I have. People are like, when you go to google.com, what happens? Which is like an extremely wide-ranging question, because there's probably like millions of lines of code that get run when you go to google.com. The first thing that happens when you go to google.com is that you type in a G on your keyboard. And when you press the G, then your kernel is like, a keystroke. And then it starts running like code for like your keyboard driver, right? And then like you press enter, and then it starts sending network packets because your TCP stack is entirely handled by the kernel. It might write files to disk. When it writes a file to disk, it needs to know two things. A, you have a hard drive, and it needs to put bytes there. So it needs to know like, how does one put bytes on a hard drive? Like, how does a hard drive work? And then once it knows how to put bytes on a hard drive, it also needs to know like, when you have a bunch of bytes on a hard drive, how does that translate into files, right? So you have like a file system implementation in your kernel. It might need to allocate memory. If you run out of memory, it might kill you dead. The killer is really exciting to watch. My partner once gave a live demo where he like ran out of memory on his machine, and then at the end of the talk, everything went dark because the kernel had killed everything. It's a really delightful feature, except when it's happening in production. So you have all of these operating systems code on your computer. But how do you call it, right? Like when you call a function, you like, I don't know, type like, you call the function, like awesome thing. So what's the mechanism for calling operating system code is system calls. So you're like, hey, I want to write a file. I have no idea how to do that. And the kernel's like, yo, I got you, don't worry. And you're just like, hey, write this string to disk. So my favorite system calls are kind of like the simplest ones. One of my favorite ones is open. So every time you open a file, you're just like, hey, open this file. And it's like, sweet, I will go do a bajillion things. You can start programs. You can change the permissions of a file. You can send data over the network to get like pictures of cats. So now we know everything about operating systems that we'll need to know. We know it does stuff. And you know that you tell it what to do using system calls. Now we're done. Now we can solve a lot of mysteries. First I want to solve the case of the missing configuration file. So who like configures stuff and doesn't know where to put the files? It's like some of you. I really hate reading documentation, kind of. I'm really impatient. I get really annoyed when I have a program and I don't know how it's configured. In particular, one thing I was talking to my colleague about recently was we were like, how do you know if Bash is using Bash profile or Bash RC? And this is like kind of a pedestrian question. And you can like look it up and you can be like, oh, well, when you log in, it uses Bash profile. And when you're, anyway, but let's say you just want to know the answer because you're impatient. So we're going to use my favorite program in the universe, which is called strace. And strace is not actually wizardry because there's no such thing as magic on computers. There's only infinite code and actually finite code. Anyway, strace traces system calls. So the way you strace is you have your program that you want to run, and then you just put strace in front. This only works on Linux, but I run Linux, so it's fine. And also all my servers run Linux. When you run strace, it kind of looks like this. Who finds this like totally interpretable? There's like 0 people. That's good, because that's like the same as me. I think the key when looking at strace output is just like ignore almost everything and then look for a thing you understand. So in this case, you probably can't read this because it's intentionally really small, but it says like libvorvis.so.0, which is like an audio library. So you're like, okay, it's doing something with an audio library, right? Like, I don't know what else is happening. And so what I can do if I want to know how Bash is configured is I can strace Bash. And I can be like, just show me all the opens. And then it's like, oh, it uses Bash RC. And also, like, there's a Bash history. And that's it. Like, we just know. We didn't need to, like, read documentation or, like, Stack Overflow. Who does that? Everyone. But, yeah. So there's some other really great system calls. There's, like, write for log files. This is kind of one of my favorite things because sometimes I'll have a program which is logging something and I have no idea where. And I'll just be like, strace. Where is it going? What's happening? We can also spy on network data that we're going to, like what's being sent and received over the network. I like strace so much that I wrote a fanzine about how much I like it, which I thought was totally normal. But I have not seen like an abundance of fanzines about it. Please write them and then trade them with me. I think I'm going to write another one soon. So I've been telling about people about strace for a while now. So I want to tell you another way to solve this problem, which is this program called OpenSnoop. So if you have a Mac and you want to see which files are being opened, you can run OpenSnoop and it'll just start printing stuff out. I'll show you what that looks like. So I run OpenSnoop and then it's just like, oh yeah, there's all this stuff happening. Like, who knows what this means? But it just shows me every time. Actually, oh, I know what's happening. So you see it's running make. So what happens is I make these slides by running make every second. So it's like make, sleep, make, sleep, make, sleep. And then we can like see what my computer is doing right now just by running this command. So this has existed, this is like basically a script, which has existed on OS X and like BSDs for a long time. And now you can get it on Linux as of like 16.04. And it's part of this like package of tools called BCC. If you look at the man page, you'll see that it's by a man called Brendan Gregg, who is wonderful, and who's like kind of like this like missionary, I feel like, who will be like, hey, I have this cool way to observe what your programs are doing. Here it is. And he just kind of like brings things from the Linux kernel to like mortals and tells us about them. And then I'm like, hey, I heard about this thing from Brendan Gregg. It's wonderful. So I get really excited about Brendan Gregg's blog, and he gives really good talks. Okay, so our next mystery is the case of the Polish website. Let's say I have this website, and when I go to it, it's like, hi, welcome to PolyConf, it's the best. But then when I go to it with curl, it speaks Polish to me, which is reasonable, because I'm in Poland, but why is it different? So this could be confusing. And so what we're gonna do to find out is we're gonna spy on our network packets. So there's this really delightful tool called TCP-dump. And what TCP-dump does is you're like, stuff is happening on my network. Can you just remember everything that happened? So just like start saving stuff. It can be good to just like put a limit on how many packets it captures, because you might run out of disk space if you're not careful. But as long as you don't run out of disk space, it's fine. I use this in production. It's cool. It's not really a problem. So I started saving the packets, and then I ran my commands. And then I spun up Wireshark. And I was talking to someone about Wireshark yesterday, and he was like, yeah, I love to use Wireshark to like assign blame. So like you have a client and a server, and something's gone wrong, and you want to know who to blame. And Wireshark will tell you who to blame. Because ultimately there's like a request and there's a response, and it's like either you sent the wrong request, or the request was right and the response was wrong, right? So Wireshark is like my favorite thing. So I opened up this PCAP file that I collected with Wireshark. And it showed me all this stuff, which, so each one of these is a TCP packet. And they're kind of going back and forth. And this by itself is like kind of a little annoying to read. Luckily, Wireshark has really good filtering. So you're like, hey, show me all of the GET requests, right? Because we know HTTP. HTTP is just text. And so you say like, hey, is there a GET in there? And it's like, yeah. Here are these 4 packets with GETs. The first one is like from curl, and the second one is from Firefox. And so I looked at the one for curl, and it understands everything, and it shows you the like contents of the packet, which is there's some like gibberish, right? Which is like n. So that up on top doesn't mean anything. But you can see here maybe that says like user agent curl 7.47. So this is what curl sent, which is cool. This is good to know. Even better, Wireshark actually like understands the HTTP protocol, so it like prints everything out for you in a pretty way, and it's like, hey, here are the headers. There's a host header and a user agent header and an accept header. This is the best. Everything is wonderful. And then I looked at what Google Chrome sent, and then there were all these other headers, and I was like, oh. Well, curl and Google Chrome were saying different things, right? Which makes sense. There's this accept encoding gzip header, which is saying like you can send like a gzip response to me, and then, oops, that's it. And then there's an accept language header, which is saying like, hey, I would like replies in English, which is a little bit hilarious because Google actually like doesn't respect this in some way. Like when I go to a different country, it's always like, do you speak Czech? And I'm like, no, it says English in my browser. Anyway, but it always like decides that I now speak a new language. So I set this as accept language header, and then now with curl, if I send the accept language header, it's now in English, and we're like winners. And we've assigned the blame to the client with Wireshark, and it's the best. I wanted to like talk really quickly about why TCP-dump is fast, because I didn't understand this for a long time. People would be like, oh, you know, TCP-dump, it's fast, it's okay, you can use it. And so you can do these filters with TCP-dump where you're like, oh, I only want things that are going to this specific IP address. And you might imagine that like filtering like huge amounts of traffic, like let's say you're doing like hundreds of megabytes per second is coming in, and you need to filter it all, and you're like, well, isn't it going to be slow and like slow down my network, and like I need it to be fast. But it gets compiled down to like, there's this like Berkeley packet filter language, and it gets compiled, and then it's actually fast. So it's like okay to use TCP-dump on your servers in general. It's like not too much overhead. So yeah, there are a bunch of network spying tools. If you're using SSL, you can use a thing called MITM proxy, which like man in the middles you. Yeah. Okay. Next up is the case of the slow program. Who has slow programs that they want to make fast? Some of you. Making slow programs fast is my favorite. I love it a lot. So I manufactured some slow programs. One of them is slow because it's spending too much time on the CPU. It's just like doing too many calculations. One of them is slow because it wrote too much stuff to disk. And one of them is slow because it's waiting for a server and just like sitting there and being like, are we there yet? And we're going to figure out which one they are without reading the code. One of my favorite things when doing this was actually just using time. Who's used like the time command to figure out how long something takes? So time is really great. The cool thing about time is that it gives you like a breakdown of where the time was spent. So it's like, hey, I was only spending 5% of the time on the CPU. So I was spending 5% of the time like calculating stuff, and then I was spending 95% of the time being like, oh, right? Like, what's happening? So there's this question of like, we have this program, it's not doing anything. What is it waiting for? So the way we're going to figure out what it's waiting for is by looking at our operating system, because the operating system knows like everything. And we're going to look inside the kernel soul. What I mean by that is like while it's waiting, there's this enter in /proc on Linux where you go like /proc / the PID of the process /stack. So I go to /proc / 31728 /stack, and it tells me like what the kernel is doing right now for that process. And you can see it's like, oh, inet receive message, TCP receive message, SK wait. What does that mean? What is it waiting for? Data on a socket. It's waiting for some network thing, right? It's trying to get a web page or something, and it's not there. So we know it was the network. It was really simple. We didn't need to like look at the program or anything. And like for a simple program, this isn't a big deal. But for a complicated program where you have no idea what your program is doing, it's kind of nice to know. You're like, oh, it's waiting on a network socket. Okay, like now I can go like back to the code and figure out what's happening. This is what our server is actually doing. It's just like, I'm going to sleep and then return, right? That's the server we were waiting for. Okay, so mystery program number 2, I ran again with time and it took like 3 seconds. And this is a pretty easy one to diagnose because like already from this we know everything. Because it ran for like 2.74 seconds. It spent 2.74 seconds on the CPU, like in user space. And you're like, look, you're just calculating something. And at that point, the operating system like can't really help you because if you're calculating things, you're like doing those calculations yourself, and you're not like asking the operating system to do them. So the answer there is to use like a Python program profiler or an Erlang profiler or Java profiler or whatever. And the program turned out to actually be doing this. So like no wonder it took a long time. Because it's in Python. If it were in C, it would be fast. I love Python. It's just, you know. So mystery program number 3. If you can do elimination, you know which one this is. But there are going to be extra mysteries in here. Actually, every time I do this demo, I find like a new mystery. Like anyway, or like a new weird thing that's happening. So this one is kind of interesting. This one is spending a lot of time on the CPU. It's spending 94% of its time on the CPU, like calculating things. But all of that is in system mode. So like the program itself isn't doing anything, but the operating system is doing all these calculations. What does it mean? If you have hypotheses, you can yell them. But I'm going to do a demo now. Is that true? Yeah, it is true. Good job. Pass, Julia. OK. I'm going to run one of my favorite programs, which is called dstat. So dstat will just like print what's going on in your system every second. So here it's printing out how much is being read and written from disk every second. So basically like nothing is happening. And then if I start running my program and look at what's happening, you're like, oh, 120 megabytes, 160 megabytes, 273 megabytes, right? It starts immediately writing data to disk, and then it stops, and then the program finishes. And then there's a mystery at the end, actually. So you notice the program stopped, and then it wrote another 470 megabytes to disk after. And this actually always happens. Does anyone know how this can happen, or why this makes sense? Buffering. You're so good. So what happens is that the operating system loves you. And it's like, I want you to be fast. I want you to finish. So it's just like, hey, no problem. It's fine. I'm done. And then it lets you finish, and then it keeps on writing. I don't know why it has to wait 5 seconds to keep writing. That's like an unknown mystery still. But there's this question of like why it takes all of this CPU. Right? Like, you're just writing stuff to disk. It shouldn't be that hard. Mostly, you're just supposed to be waiting for the hard drive. So what's going on? I was very surprised by this. So what we're going to do is we're going to run a program called perf, which is one of my favorite programs. I even have a sticker that says perf. It's actually from BuzzFeed with like OMG perf. Anyway. I think that's funny. So I start running my program. And then you see at the top, it says AES-NI ENC1 and eCryptFS write begin. So AES is like an encryption thing, and eCryptFS sounds like an encryption thing. So what's actually happening, kind of interestingly, is my program is writing to disk, but it's writing to an encrypted partition. So it's super slow. And when I took this file, so this program takes how long? Let's see. I think it takes like 4 seconds. Boop, boop, boop. Yeah, 4 seconds. So it says 4.61 elapsed. This is kind of small. I'll make it a little bigger. Oh God, what is a computer? Okay, yeah. So this takes like 4 seconds. And then I wrote a version like mystery4.py. Which just like literally writes to a different file, which is not encrypted. And then this one only takes less seconds, like 3. Anyway, it gets faster. And then it's only spending 20% of its time on the CPU. So you can see this number, like 93, went down to 20. I get really unreasonably excited about things like this. Okay, so that was cool. We used perf-top and we won. We solved our mystery. I want to talk about dstat for a second, because I think it's not totally obvious why this is so awesome. So once I had a database, and the database was misbehaving. It was slow, but really sporadically. Every so often it would get really slow, and then there would be these errors, and I would know what was happening. And so eventually I tracked down which machine it was on, which database box was having the problem. And I still don't know, and I asked the database team, and they were I don't know, but they were willing to help me, but they just didn't know offhand. So I wanted to investigate more and figure out what was happening. And so I was well, databases do I/O and they do network stuff, so I'll just run dstat and just stare at it. So I ran dstat, and I kind of waited for it to become slow, and I just stared at dstat for I don't know 10 minutes. It's a really exciting life. And then at some point when it got slow, you would see it would get hit with 500 megabytes of data that would come in over the network. And then it would get slow again, and 500 megabytes of data would come over the network. And it would get slow, and 500 megabytes of data would come in over the network. This was happening every time. So I asked someone, I was hey, I think that there's something that's sending us way too much data. Do you know what it is? And he was yes. And then he was this is the culprit, and I know, and I knew this was going to be a problem, and then we totally tracked it down. But we tracked it down using dstat, right? And just by looking at what was happening on the machine, because everything happens for a reason, right? And that made me really happy. And then we fixed the problem, and then it didn't happen again. I also really love perf-top because it just tells you what's happening on your machine at any time, which I think is kind of wonderful, and it's something that I didn't realize was possible, kind of, before. I didn't realize you could just be hey, these are the functions that are running, right? This isn't these are functions inside my computer that are happening right now. It's like I'm doing malloc, or like, I don't know, it's like top, but for functions. It's crazy. I had no idea. So, yeah. But the kind of cool thing about perf top is that you would think that like it kind of only works with C, and I'm talking about like systems. You're like encrypt.fs, blah blah blah. Julia, like I'm like a Ruby programmer, or I use Node, or I use like Clojure. What am I supposed to do with this, right? I promised you it's for everyone. So the really wonderful thing about perf is that there's this thing called perf map agent, which will like which will like look at your JVM process, so like your Clojure, or Java, or Scala process, and then say, okay, when this is happening, I know that it's this Java method, and then you can use something like perf top and collect performance information in a way that's like really fast, and then you don't need to like connect with a debugger, like with a JVM debugger, and it also works with Node. I think Node has like perf support built in. So this is just like this really cool tool which like works really well with C stuff, but it also works with Java and Node. It works a little bit with things like Ruby. So sometimes I'll be like, hey, I have this really sad Ruby process, and then I'll run perf, and then I'll see like, I'll look at the top methods, and there'll just be like something in the Ruby virtual machine, or like the Ruby interpreter. Yeah, in the Ruby interpreter. Which is not necessarily that helpful. But sometimes it's like, oh, I'm like garbage collecting. I'm like, okay, you're garbage collecting. Maybe I'm making too much garbage, right? So it can give me like some hints, but it's most helpful with things like the JVM and Node, because then it tells you like the Node function. That's your problem, and then he can go like fix it like a wizard. And the good thing about these is that you don't need to like instrument your program in advance. Like your program is running, and then you just like bring in perf, and then you're done. It always works. The other cool thing that you can do with perf is you can make these graphs called flame graphs, which are my favorite graphs in the universe. So basically what this means is like each wide thing is a function, and then that's like the amount of time that function was running for. And I just really love these graphs. You can make them like you can make them with a lot of different tools actually. If you Google flame graph, and they're a really good way to see like where you're spending your time. So here it's like there's this function ticket spin lock in the middle where you're spending all your time. This is something that was waiting on a lock. And an experiment I did with Rust. So yeah, so maybe I've motivated you to think that your program is a black box. I think I have 10 more minutes. I might tell you more things. So yeah, there are a lot of amazing tools. One thing that I forgot to tell you about Wireshark, which I really wanted to remember, because Wireshark, oh no, Wireshark is over there. Yeah. Okay, Wireshark is over there. So one cool thing about Wireshark is Wireshark knows about HTTP. If you're making database queries and you want to know like which database queries you're making, you can actually, so let's say you're making like Mongo queries or Postgres queries. Wireshark knows about these wire protocols. So you can collect some traffic and then just be like, which tables was I querying? And it's like, oh, you were querying these tables. And you're like, what? Like, I don't need to like instrument my application to know which tables I was querying. I can just find out like magic. And I've totally used this because I had this application and it was doing this weird database stuff and I wanted to know. And I was just like, oh, now I know. Like, now I'm a wizard. I don't need to edit the code. Editing code sucks. And so the thing I really like about investing in these tools is they kind of like pay off across like all the languages I work with. So we have like 10 more minutes. I might tell you another thing. I did this weird thing where I thought I might have extra time, and I wanted to tell you something else that's unrelated. I hope that's cool. Oh God, how do I use a computer? I wanted to tell you about like experimenting with programming. Who likes to learn things? Why else would you be here? I wouldn't understand. I really like to learn things. I want to tell you about some cool stuff I learned that's like kind of, I mean, this is sort of related. Anyway, I want to tell you about some cool stuff I learned. And I want to tell you how I think about learning things in a really fun way. So rule 1 of programming experiments is it doesn't have to work. You also don't have to finish it. And I find this like really helpful when I'm trying to be like, I want to know how a database works. And I'm like, sweet, I'll write a database. Which like, obviously like you don't have time for, but you can still do it anyway. A really fun place to do this stuff is the Recurse Center, which I went to 3 years ago. I kind of like learned about this there, and I turned into a person who could learn things like by magic. It's like the best programming community in the world, I think. Not that, anyway, it's like really wonderful. And you spend 12 weeks, and you're like, I'm gonna learn cool things about programming, and then you learn whatever you want, and then you're done. So I want to tell you about a thing I did, which is once I wrote an operating system, the key thing you have to remember is that it doesn't have to work. And it didn't, so it was good. Because I was like, oh, what's really hard? And I was like, I don't know, I'm like not scared of like new languages, and like I don't want to learn like Clojure. I love you Clojure people. I just didn't want to learn Clojure. I wanted to like learn something that I thought was like really scary. And I was like, well, operating systems are really scary. So I told someone, hey, I want to write an operating system today. I told this to Lindsay Cooper, and she was like, okay. Yeah, you should do that. You can maybe do it in Rust. And I was like, I don't know what Rust is. Like, anyway, I'd never written it. So I wanted to do it. And kind of one thing that I realized when I was trying to do it is if you write an operating system, then you lose everything. And you're just like left in this sort of like pit of despair where you're like, I don't have a hard drive or files or processes or a working keyboard. Oh God, and it's like really exciting and terrifying, right? So I was like, okay, I'm just gonna write a keyboard driver so that I can press like J on my screen. And then, so I spent like 5 days trying to do this, and it would just crash. Like it would crash for 5 days every time I tried to press a key. And I would like try different stuff, and I would read a wiki, and it would still crash. And I was like, oh, this is what like systems programming is like, right? Like when you read this thing about like James Mickens, who's just like, web developers live in this world of rainbows, and then like, anyway. But it's not true. Web developers do not live in a world of rainbows. Now I'm rambling. Cool. So one thing that you don't have when you build an operating system is malloc. Like you can't allocate memory. This is really fun because you can allocate your own memory. And you can just be like, hey, you need to return an address, so I'll just always return 42. This is a totally valid function that you can use, right? Like you can do this in your programs today, right? You can just be like, hey, malloc, it's 42. So you're like, I did this in Rust, whatever. So you're just like x equals 5, and then x equals 5, and then you're like y equals 88, and then that allocates memory, and now x is 88, because you only have one variable. And this is really silly, right? Like it takes like 5 minutes to do, but I think it's really fun. Because then at the end of it, you're like, oh, now I know all these things about memory allocation, and I have like a stronger mental model of how it works, which is just like, you just have this function between you and the abyss. So like I learned a lot of stuff about how to do that, about how to like write a kernel. One fun thing about this was that like Rust was kind of confusing, but the Rust like IRC channel was like extremely helpful, and I would be like, I don't know how string works. Also, I don't know how assembly works. Help! And they would be like, we will help you. And I'd be like, this isn't even a Rust question, but can you help me anyway? And they were like, yeah, obviously. And they were really nice, and I like succeeded in doing things. One weird thing that happened when I did this is someone emailed me and they were like, hey, do you want to like maybe like interview with the like kernel performance team at Apple? And I was like, I literally just wrote like malloc, which returns a constant. Like, but then the weird thing that happened was like I learned like a little bit about this stuff, and then we did like a phone screen, and they were like asking me about like memory and like memory mappings and like how do you have multiple processes? And I was like, oh, I know like the basics of this because I just like struggled against it for 3 weeks, and then I like totally passed their phone screen, which was weird. And they were like, we think you know things, and I was like, maybe I do know things. We're gonna get back to that anyway. But yeah, I learned that like file systems are hard because you actually have to write them from scratch, and like there's a reason operating systems are millions of lines of code. Okay, so we're also going to talk about databases because we still have 6 minutes. So let's say you want to know how a database works because you've been using databases, but you want to know how it works. And so I made this database, which was called fun.sqlite because SQLite is like the best, simplest database. And then it had like all the words in English in it. I just put 3 there because I had to type them. So one cool thing you can do to understand how a database works is you can just like cat your database, like just like print it to the screen. But there are words in there, like Acapulco. So that was cool. I was like, oh, a database is stuff with text in it, like ASCII text. But this was not like super helpful. I read about this a little bit, and it was like, oh, a database table is a tree, like and there are nodes in it that are connected in ways. And I was like, okay, that's cool. So I found the SQLite source code, and I didn't understand it, but I kind of like grepped a while till I tried to find a place where it like went into like parts of the tree, and I just put a print statement in the middle. And when you put a print statement in the middle, you can run like select star from fun, and then it'll like run your code. So you can just put your dumb code in the middle of SQLite's smart code, and then run like queries and see what happens. And it totally worked. It was like, oh, this like ID 1 is like at the bottom of a tree, and it's like 7 levels deep, and it starts at page number 1. It turns out that it almost starts at page number 1. This one, 80,000, went from like 1 to 5, and then it went in like a different direction. And that was really cool. And then I felt like I knew like how SQLite worked a little bit. I spent like 1 or 2 days on this, right? But I felt like it was better. Like I don't really read books that well or documentation. You might have learned that I'm sort of impatient. But I could like edit the SQLite source code, and I was like, oh, now I know that like there are trees and there's pages, and like they try to be smart. I still want to like figure out how it does joins and like put some print statements there and see what happens. Another thing I did once was I wrote a TCP stack. We have 4 minutes. This is perfect. In Python, right? Because I was like, I'm not that good at C. Let's see if I can write a TCP thing that like talks to Google.com in Python. And then a year after I did this, Gary Bernhardt one day tweeted, he was like, your homework is to implement UDP in Python using raw sockets and get another machine to talk to you. And the cool thing about this, which I found surprising, is that, so this took me like a week to do. And I don't want to be like one of these people who's like, hey, like everyone should like implement TCP from scratch and understand how floating point numbers work, because that's like really annoying. But the point is that like if you want to implement TCP from scratch, like you totally can, and if you want to know how floating point numbers work, you totally can. Like, and like you can figure it out, and then you end up actually knowing things, which is kind of weird. Yeah, so I had this code that you can't really read, but it's not important. But I was like, yeah, I'd make an IP header and TCP header, and then I would send a packet to Google, and Google would be like, yeah, you did it right. And it would send me a response, and then like I wouldn't reply, and it would be like, connection closed. Like, I'm bored with you. And then I learned how TCP, one other thing that happened when I tried to talk to Google is I was working in Python, and Google obviously has like an actual fast TCP like server. So I would send it packets, and it would be like packet, 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 and I'd be like, packet? And it would be like, and it was like way faster than me. But you can write something that like doesn't really work, but that like works well enough to like get a web page. I got a web page from google.com. It was amazing. And Python could not keep up, completely unsurprisingly. How are we doing? We have like 0 minutes left, so I'm gonna stop. Oh yeah, I like write down my, like when I try to learn things, I like write them down, which is fun, because then people tell me new things normally. And the kind of cool thing is that like I found out that like if I do enough weird experiments and try to learn stuff, then I end up at the end of the day like actually knowing things. Then I talk to people and they say like words about operating systems or like whatever. I'm like, oh, I know what you're talking about. Cool. You too could know stuff. I'm not going to do questions. If you come to me with a question, I will give you a prize. The prize is a zine about S-Trace. But yeah, no questions. No.
Hello. First of all, thank you for an interesting talk, and I hope all developers will strive to know their tools and OS as you. On the other side, I want to ask, do you have some experience with Dockers and debugging Dockers, or programs on Dockers? And second part, how do you usually debug running server? So when S-Trace is not an option.
So the first one was about Docker? Did you say Docker? Yes. I don't debug Docker, so that's the answer to that. But how you debug your running server? So when you say S-Trace is not an option, that's true. That's really important. Because S-Trace will like slow down your program by like 50 times, which is a problem. But So one thing about a running server is sometimes my running server will already be in a really bad state. I'm still strace it anyway, because I'm like, well, it's really bad. I can't make it worse. These tools so this tool OpenSnoop I demoed is based on this Linux kernel mechanism called eBPF, which is coming out in like newer kernels, like 4 point something. And that's something that you can actually use. You can also actually use perf. And there's this system in the kernel called ftrace. Anyway, there are like a bunch of things that you can actually use on like strace. Yeah, that's all for questions. Thanks.